So now let's specifically define the quantities voltage and current in terms of trigonometric functions or periodic functions. All AC voltages and current can be written as sinusoidal functions. An alternating current is a function of time, also called the time domain expression. Now it's written as I of t, or the current as a function of time, is equal to I max, also called the peak value. Sometimes you'll see that as I sub p, times the cosine of omega t, or the angular frequency times time, plus whatever phase shift happens to be associated with a current waveform, plus phi sub I. And alternating voltage, written as a function of time, will be written as v of t. So the v of is the function operator, v of t, again equals v max or v peak times the cosine of omega t plus phi related to the voltage. So these are the formalisms for what we call the time domain expression for the current and the time domain expression for the voltage, right? They take the peak value, you then multiply the peak value by the cosine. The cosine argument gives you both the frequency information and the phase information. The subscripts on the phase angles here on phi I and phi v indicate that the current and voltage do not necessarily have the same phase in AC systems, meaning that the peak values do not have to be coincident. So for this discussion, let's focus further on the voltage function for a minute. This v of t equals v max cosine of omega t plus phi sub v. Let's look at that. The quantity v max is the maximum value or amplitude of the voltage. Since the sine and cosine functions are bound between positive and minus 1 by definition, the Vmax term just serves as a multiplier, right? So we take the sine wave, which is bound between 1 and minus 1, we multiply it by Vmax or V peak, and now all of a sudden this sine wave oscillates between plus Vmax and minus Vmax, right? So the peak value of the waveform becomes the peak value of the voltage, and the peak-to-peak value is twice the max value. So here we see that time is measured in seconds, and when multiplied by the angular frequency of omega gives the time as an angle. In the simplest case, there is no phase shift, meaning that phi is 0 and the curve starts at the origin. More generally though, phi represents a shift of the curve to the left by an angle. Phase shift does not affect either the frequency or the amplitude of the waveform and only amounts to a difference in what time is considered in 0 in comparison to some reference time. This will become more important later when we consider the relative timing of voltage and currents and how they are affected by the properties of materials and electronic devices. So here we have some examples of some really simple phase shifts. Here we have a phase shift of 90 degrees. We would say that A is ahead of waveform A here, is ahead of waveform B by 90 degrees. This is actually the difference between sine and cosine, a 90-degree phase shift, right? When sine is at its minimum value, cosine is at its maximum value. When cosine is at its minimum value, sine is at its maximum value. What we would say in this form is that A leads B. The verbalism there is A leads B. Here we have another phase shift of 90 degrees. In this case, B peaks before A, and so we would say B is ahead of A, so we say B leads A by 90 degrees. If we have a phase shift of 180 degrees, waveform A will peak when waveform B is at its minimum, so we say that they're mirror images flipped around the time axis there. If there's 0 degrees phase shift, waveforms A and B are in perfect symmetry with one another. And I know that we indicate 90 degrees and 180 and 0 degrees, but phase shifts can be of any degrees, right? You could have a 1 degree phase shift or a 200 degree phase shift. And phase, again, can be measured either in units of degrees or in radians, right? It's an angular measurement. So in summary, the voltage function V of t equals V max cosine of omega t plus phi sum v has the following parameters. Vp, or V max, is equal to the peak voltage. This is the maximum amplitude of the sinusoid. Its units are volts. Omega angular frequency. What does omega measure? It measures the speed at which the sinusoidal function is oscillating. Its units are how many radians are transversed per second. Rads per second. Terrible radian. RAD per second. There's another way to measure the speed at which a sine wave repeats itself other than angular frequency, and that's ordinary frequency, more commonly just called the frequency. Units are in hertz. And remember, the relationship is angular frequency equals 2 pi times frequency, or otherwise you could write F equals omega over 2 pi. T is the period. It's the length in seconds that it takes the waveform to go through one cycle, so period. It's equal to 1 over the frequency. It's just the inverse of frequency. Its units are seconds. And finally, we have the phase angle. It represents a shift in the sine wave, either left or right. Its units are radians or degrees, whatever you happen to measure omega times t in. So how do these different quantities manifest themselves in the U.S. power system? This is a modern energy systems course, so how do these different quantities, peak, phase, and frequency manifest? What are we going to generally experience? Well, voltage and currents in the AC power system have a variety of peak values. Typically, voltages are standardized at levels for generation and transmission. For example, the value of the voltage of a residential wall outlet is about 170 volts peak and has a standard AC frequency of 60 cycles per second or 60 hertz nominal. Regarding phase, in the US, 3-phase systems, 3 voltages of the same magnitude are transmitted together that have a phase separation of 120 degrees. So, if you were to measure wall outlet at 3 different locations, they should all be 170 volts peak. They should all be 60 cycles. But compared to one another, they may have phase differences of 120 degrees. So compare one to another, it may be 120. Compared one to another, it may be 240. Just depends on what phase you happen to be connected to, since there are 3. In practice, current and voltage waveforms in the power system are not actually precise sinusoids. While they're always periodic, they are not always rounded and or smooth. This deviation from the sinusoidal shape can be accounted for due to harmonic distortions or frequency distortion by loads such as power electronics, and also due to the limitations of the generators.